Good? Thanks, Guru. All right, so today we're actually going to get started with the material for the class, which is fun. We're going to start talking about one of the sort of key abstractions that operating systems provide, which is the process. We'll just get right into it, get our hands dirty using some standard Linux tools to sort of poke around inside processes and start talking about the stuff we're going to be covering this semester, right? So there's a couple of brief announcements. If you're not receiving email for the class, I don't know the last time I sent something to this list, but I've been updating it as the registration changes. If you want to be on it, though, at some point I'll stop updating it, and then if you're auditing the class or you just want to know what we're doing, you can go and sign yourself up, and you'll stay put. So is everybody getting email for the class if you think you should be getting email for the class? OK. Several people have discovered that they, in order to log on or sign yourself up for the Piazza forum, you need an access code, right? Guess where that access code is located? It's on the class website, right? It does require some reading comprehension skills to find it on the class website. Not a huge amount of reading comprehension skills, like nothing that's going to, earn you any awards or anything. But that's sort of the question we've been getting, where the answer is, RTFM, right? Read the friendly website, right? All right, so thank you for taking the preterm on Wednesday. Again, this is really helpful metadata for us. And we posted some stuff after the exam about exam procedures. It's going to be a little bit tricky getting exams done in this room. It's pretty small, right? Or I should say, you guys are big. The room is the same size it was last time I taught in here, but there's more of you. The TA office hours and the extra recitation, quote unquote, that we're going to be holding, we will be scheduling over the weekend. So if you haven't taken the Doodle poll, please go and do that so when we can find the best time. We will probably hold that extra recitation at the time that gets the most votes. I can't promise that everybody will be able to make it. And then we'll hold the office hours at other times to be determined throughout the week. So it looks like we're going to have lots of office hours. The add and drop deadline and office hours and recitations will all start next week, right? So by Monday, we should be running at full steam with all of our weekly activities with office hours and recitations. Finally, the add drop deadline is Monday. So if you're still not sure about whether you want to take this class, you have the weekend to work on the assignments, look over things, and just try to make a decision for yourself, right? I want everybody to stay in the class, right? I guess the disadvantage of being prepared is that it's possible that people are sort of finding out what they're going to be in for earlier than they did last year, which might make people nervous about taking the class. But I really want you guys in the class. I'm not saying this because I'm trying to reduce your numbers any further. I'm kind of sad that some people have already left. But I do want you guys to know what you're getting into and be able to take this course in a semester where you can do well and really learn as much as you can, right? Any questions on this sort of administrivia stuff? No? Good. OK. I feel the need, unfortunately, and this has been updated on the website, to make a clarification that I don't think is really necessary with respect to the collaboration policy. But just let me be even more clear about referencing other sources, right? So if you guys have written papers for other classes, you might have footnoted things or referenced something or even quoted a few sentences from another text in support of one of your arguments. And I guess there's people who think that, hey, the equivalent for a programming assignment is finding someone else who did it and cutting and pasting a big blob of their code into my assignment and then putting a comment in there saying, like, I cut and pasted this code from this GitHub stuff that I found, right? So that's not OK either, right? I just want to make sure this is explicit and we've covered it so that we won't have any issues later, right? This is common sense stuff, right? If you think you're cheating, you're probably cheating, right? If you're worried about what you're doing might be cheating, you're probably cheating, right? So, but I just want to be clear about this so that we don't have issues later. Any questions about this? This is pretty normal. You are welcome to ask the course staff if there's a little bit of something from the internet you want to use. Our first answer will probably be no. Our second answer will probably be no. And then we can go from there, right? But you can sort of pretend for the purposes of doing these assignments that you're working in sort of a clean room trying to implement these things from scratch. That's the point. That's how you're going to learn. Yeah?
What's around like code snippets? Like you do sort of Stack Overflow for a quick line or two that you're trying to do.
Again, that stuff is probably OK, right? I mean, if it's like, I don't know, counting the number of characters in a string or something like that, right? Like that sort of thing. Where you would assume this would be kind of common reference material. But if you're looking on Stack Overflow for solution to assignment 2 for CSE 421, right, and then cutting and pasting that, that's probably a problem. If you have a question, please ask us, right? And note that because the TAs don't read most of your assignments, in fact, any of your assignments, putting comments in the assignments is not sufficient to inform us of anything, right? The submission checker doesn't know how to read yet, right? I'm working on that, but it's not done yet. And maybe won't be done this semester, but it cannot parse your comments. So if you feel like you need to tell us something, don't hide it in the comments somewhere. We'll never see it, right? When I took this class at Harvard, actually, the TAs did read some of the assignments, and one of the students decided to test this by putting a comment in that said to his TA, if you read this, I will get you a 6-pack of beer, right? And the beer was delivered to the TA, right? All right. OK, so last time we started talking about some of the things that operating systems do. There were two things, right? One thing is up on this slide, right? Operating systems provide abstractions that make hardware easier to use. Does anyone remember what the other thing that operating systems do was? I'm not going to pick somebody with their hand up. I'm going to pick someone with their hand down. Do you remember? Were you here on Monday? Do you remember operating systems do two things? One is provide abstractions. The other is what? Multiplex hardware resources. Yeah, that was good. He didn't even raise his hand, but he knew it. That's a new strategy. OK, but today we're going to talk primarily about abstractions, right? Because the thing that we're talking about first, which is the process abstraction, is really entirely an abstraction, right? There's no sort of hardware resource being multiplied by processes. Processes are instead an abstraction that we use to organize other information about the system, right? You guys have programmed for years. And you've probably used lots of abstractions already. So can someone tell me something about the abstractions you've used? What are they for? What's one thing that abstractions do?
They hide layers that are more complex.
Yeah, they hide complexity, right? I'm going to take the front and the back of that answer and sort of put them together, right? And frequently they do this in a layered fashion, but they are definitely frequently there to hide complexity, right? What else do abstractions do? Yeah.
They turn more complex problems into divide and conquer solutions.
Yeah, so they create sort of separation of concerns, right? They allow you as a programmer not to have to know about how everything in the system works and essentially be able to use an interface that has a well-defined sort of API to it and trust that other things are going to sort of take place as they're supposed to. What else do abstractions do? Yeah. Yeah, so the idea is that I can take code that was written on one system making one set of assumptions and move it to another system. And the reason is that code is using an API that may be supported on both systems in very different ways, right? What's one example of that you guys are probably familiar with? Of code, what sort of 1980s era technology, maybe was designed to make code more portable? You guys have all used this. Some of you, since the first day you were here at UB. Yeah?
Java virtual machine?
Java, right? The Java virtual machine, right? Write once, run anywhere, right? Including in these terrible applets that some websites are still trying to get you to run, right? So it was a great idea, right? And a little bit dated now. We have some new technologies and a different way of looking at things. So right, some of the things that abstractions do you guys have got, right? But in general, this is what it is, right? We want to hide undesirable properties, right? We want to sort of hide the properties of certain parts of the system that we don't like and try to preserve the ones that we do like, right? Abstractions can also frequently add new capabilities. So they can create the ability for some underlying piece of hardware, in the case of the operating system, to do something that it couldn't do, right? And then finally, abstractions frequently exist to organize information about the system, right? To sort of create an area of concern where sort of several things get sort of bundled together, right? So we'll talk about all of these three things today with respect to an abstraction we're going to talk about, which is the process abstraction, right? And also, so abstractions frequently provide an interface, right? So interfaces, right? How many people have used an interface before? Yeah, hopefully everybody, right? This is an arm exercise type question, right? So what is an interface? Who can define an interface for me? What is an interface and what do interfaces do? You guys have all used them. Why have you used them? What's an interface?
Like a GUI system where you can just call the function. You don't have to worry about how it's implemented.
Right. So you can just call some function in an interface and not worry about what it's implemented. However, what do you need to know about that function? What does that function actually have to do for you to call it, right? OK, great. Now I have a function, and I can call it. Now I have to worry about what it does, right? But I probably am worried about what it does, right? Why would I be worried about what it does? Yeah, or either one of you, whichever one comes up with it. This is potentially a trick question simply because I called it because I wanted to do something, right? Like some specific thing, not anything, right? So interfaces provide guarantees about what a particular part of the system is going to do, right? And allow the programmer to not worry about how that's getting done, right? And one way we talk about this is they separate policy from mechanism, right? And we're going to come back to this split often when we talk about operating systems and system design in general, because this is a really, really important design principle. It's a very powerful design principle, right? The separation of policy from mechanism. Policy being guarantees about what's going to happen, mechanism being actually how that thing gets carried out, right? And someone earlier talked about portability of moving code between different systems, and separating policy from mechanism allows us to preserve code on one system that makes assumptions about policies while the mechanisms may be very different, right? So policy, what the interface commits to doing, from mechanism, how that's actually done, right? OK, so let's talk about an example abstraction that's relevant to operating systems. I picked one that we're going to come back to in like 2 months, by which point all of you will have forgotten this discussion, right? So we can talk about it now, and then when we get back to it in April, it'll be review, right? How many people have used a file before? Maybe not everybody. It's a little old-fashioned, right? I mean, now we have these cloud things and stuff like that. So it's not always the case that people are really exposed to files in the same. How many people regularly sort of navigate the file system on their machine? OK. How many people do that in a command line environment? OK, a number of hands keep going down. I mean, you guys have used files all the time, right? So this is probably a nice abstraction to start with because you're comfortable with it, but you may not have thought hard about it, right? So what are some of the undesirable? So first of all, what are files abstracting fundamentally, right? What piece of hardware on the system is the file abstraction? Was the file abstraction originally designed? The file abstraction has been sort of tweaked and coddled into doing lots of things it wasn't really originally designed to do. But what was it originally designed to do? What part of the system was it designed to be an abstraction of? Yeah. Don't know. A file. Where are files stored on your system? Where do they live? Storage. Where are they stored? Storage. So that's a good answer. I hear the hard drive, right? So again, think about abstraction, hardware, right? What part of the system, if I pulled it out, would all the files be gone, right? That would be the disk, right? So files were originally designed to abstract disks, right? Who has a really detailed knowledge of disks and how they work? OK, good, nobody, right? But let's make some guesses, right? So what about the disk might the file abstraction want to hide? What might be undesirable properties of a spinning disk or a physical disk that files might want to hide? Yeah. Right, so disks actually consist of these blocks, right? Blocks of bytes. And the blocks of bytes are going to be located all over the disk if it's a spinning disk, or if it's flash, there's still sort of locality to some of these drives, right? So the part of the file that looks contiguous to you might be located all over the disk, right? What other undesirable properties of disks might we want to hide? Yeah.
The address spaces where files are stored are long numbers that are hard to remember, where when you name a file, you know what's in it.
OK, yeah, so right. I mean, disks, do you think disks understand the names that you give to files? No. What do you think disks understand? Like, not memory, numbers, right? Block 2462, right? The disk has no idea what file that's part of or even what it is, right? And so there's this translation that goes on. And so, yes, if you had to name all your files in numerical order, right? This is the first day I get my computer, I start with file 0, right? And I go 1, 2, 3, 4, 5. That wouldn't be a very sort of, does anyone remember CompuServe used to have email addresses that were like phone numbers? Am I the only person that's this old? Yeah. One of the original email providers thought, I guess, that people would like to have email addresses that were like their phone numbers, right? Except that phone numbers are terrible, right? And they're hard to remember, and they don't make any sense. So they gave out email addresses like 025386 at CompuServe. And amazingly, that wasn't very popular, right? When other people were getting like the man at gmail.com. All right, so addressing, right, is another thing. The other thing that no one got to is disks are really slow, right? And files can hide this property by doing a lot of caching and doing some smart things to try to optimize for disk operation, right? And disks also can fail, right? And a lot of file systems do things to try to avoid or mitigate the effects of disk failure. We're going to come back to this, but I want to use this as an example to talk about abstractions, right? What new capabilities do files add, right? What can you do to a file that would be difficult to do if you were trying to interface to the disk directly? Yeah. What's that? Yeah, I can move a file, right? And moving a file, essentially, when we talked about it before, is just altering the name, right, that I'm preserving in the abstraction, right? That doesn't necessarily have to involve the disk very much at all, right? What else can I do to a file that would be difficult to do on the disk? Yeah?
Modifying the content?
Well, I could do that on the disk, right? But what can I modify about the file that would be hard to modify if I was trying to interact with the disk directly? What might I want to do to the file? Permissions? OK, so that actually is an example of a new capability, right? The disk doesn't know anything about permissions. I heard the answer. Size, right? I want to grow the file, right? I picked some blocks on disk. On disk, I've got 3, 4, 5, and 6. That's the part of my file, right? Now I want to grow it. Well, where do I go, right? 7 is already in use for something else, right? So the ability to grow files, shrink files, reclaim space, right? These are examples of new capabilities. And finally, what other information do files organize about the abstraction of sort of a blob of data, right? Now, clearly, files themselves as an abstraction directly organize data, right? That's what's in files, right? But what other data gets attached to files that's potentially useful? Yeah? Names, timestamps, permissions, all this sort of metadata, right? And this is stuff that's potentially useful to the people who are using the file abstraction, right? So again, so this is an example of an operating system abstraction. It's a forward pointer. We'll come back to this later in the semester and talk in detail about how disks and the file systems that are run on operating systems actually provide those properties, because it's kind of a fun story, all right? So this is essentially what we're going to spend this semester doing, right? We're going to talk about threads, which is the abstraction that's attached to the CPU. Pretty much every piece of hardware on your system has some operating system abstraction that's been built to accomplish the type of things that we just discussed, right? For the CPU, we have threads. For memory, we have the notion of address spaces, which we're going to talk about in about a month. And for files, for the disk, we have files, right? However, there's this organizing principle that operating systems apply to all of this stuff, right? And that is called the process, right? It's also called other things. Can anyone give me sort of synonymous names with process? Yeah. Could be called a job. That's a good one. That's old school. Yeah. What else? What? Task. Linux calls these tasks. What else? What do you guys probably think of these as? No, threads are, what's that? Programs. What else? I still haven't heard the most common one, right? Application. Yeah, there we go, right? So I launched Firefox, right? Firefox is an application. I wouldn't call it a task. But that's kind of what Linux thinks of it as, right? And the idea behind processes is they organize a lot of the other abstractions into one sort of protection boundary, right? So this is, and this isn't going to make sense to you guys yet, but this is our friendly process diagram, right? And because I'm lazy, we tend to use this one over and over again, right? This is our process. It has an address space, which is the abstraction of memory. It has a thread, which is abstracting the CPU, and it has maybe some set of files, right? Processes on some level are the most fundamental and most important operating system abstraction, right? I don't know. I don't know if I agree with that statement, actually, even though these are my slides. But it's the one we're going to talk about first. So it's the most important for today. But processes exist to sort of organize information on the system. And the system also provides a set of guarantees and capabilities to processes to allow them to use system resources in sort of a coherent and safe way, right? And yeah, I mean, so you can think about this as something that the computer is doing, right? Like an app, like a task, right? Yeah, OK, we did this a little bit, right? So processes. So this is what sort of processes are the container for, right? And again, unlike some of these other abstractions, they don't map down to hardware, right? They map down to bundles of hardware, right? Processes, as we're going to describe them this semester, can contain one or more threads, right? A thread of execution. They contain an address space, and they can contain some number of open file handles, which are a representation of a file that the process has in use. All right, so again, so these are not tied to hardware. Well, hold on. So that's our thing again, right? So now we have so here's my threads in the process. I've got my address space, and I've got 2 file handles here, right? One of the most fundamental things that operating systems have always been built to do, right? And we'll talk more about the history of operating systems later in this semester. But one of the most important things that operating systems have always attempted to do, tried to do, with some successes, some failures, is provide isolation between processes, right? Why do you guys think this is the case? Think back to the dawn of computing. Yeah.
Well, so there's no like I don't know, memory flaws between like them sharing memory, or you could kill off one process without messing up another one.
Yeah, so certainly if I have a badly written or badly behaved process on my system, that could cause a lot of troubles for other processes. Early versions of Windows didn't really have any notion of memory protection, and so it was very easy for one process to sort of corrupt the state that was in use by another process. If I'm that helpless process, I don't really expect that to happen, and so I probably do something bad, right? Or crash or whatever. But think about the earliest computer systems, right? Maybe not quite the earliest, but the very early computer systems. What was probably a lot different about them than the ones you guys use today? Yeah.
Most of them were multi-user operating systems.
Yeah, so most of them were designed to support multiple people, right? And that's because at the time, computers were these really expensive things, right? My guess is that some of the machines you guys probably own are more powerful than Timberlake, right? I mean, that's not necessarily a high bar to get over. But the point is that now we all have these personal computers that are incredibly fast, right? But at the time when these big sort of shared user mainframes were being deployed, those computers were really, really expensive, and certainly out of the range of individual people being able to purchase, right? And so your department purchased one of them. They put it in this special room behind a lock and key. There were only a couple of people who were allowed to sort of access it directly, and the rest of the people used it remotely. And what it meant was that you had a lot of people on the computer trying to use it all at once, a lot of people running different processes, and it was really important to make sure that no one person could inadvertently or vertently disrupt the operation of the entire machine, right? Nowadays, problems with isolation between processes tend to be more annoying, right, than they are. But what else? What other type of issue could occur if I allow more communication between processes than I might want? Yeah. Yeah, I could have some pretty serious security flaws as well, right? So if I allow processes to read each other's memory, I might have a process sort of, squeezing credit cards out of another one, right, which would not be cool. All right, so, but in general, the way that operating systems have been designed is that they are, they make communication between processes quite difficult, and they make it be done so these very, very well-defined ways. And we're going to go over a couple of them today, right? Inside of the process, that's the process's own problem, right? So operating systems, they make the inter-process communication very easy. Sorry, I always get inter and intra mixed up, right? The intra-process communication, the stuff that goes on inside the process, that we want to make as flexible and as easy as possible. But if you mess it up, it's your problem, right? And what happens is your process crashes, and the rest of the processes on the system go on happily, right? Communication between processes usually requires coordination between those processes, and is done with some degree of finesse to avoid sort of processes being able to disturb each other, right? Any questions about this before we go on? Right, so this is one of the things. So when you think about processes as encapsulating these other abstractions, the reason we're doing this is basically 2 reasons. One is to organize the parts of the system that are involved in doing one thing, right? Your web browser versus your email client. The other reason is to protect those 2 applications from each other, right? All right. So and this is the intra-process communication slide, right? So if I want to share data in one process, that's pretty easy, right? Most of the threads running in one process have access to all the same data structures and parts of memory, and so this is quite easy to do, right? And we'll come back to making this safe when we talk about synchronization more in a week or 2, right? So there are issues with doing this well when I'm sharing data within the process, but this is something that we'll come back to when we talk about synchronization. But today I want to focus on this inter-process communication, right? So if you guys have done, any sort of programming in Unix or really any sort of environment, you may have dealt with some of these IPC mechanisms, right? So we'll talk a little bit now about how we communicate between processes on the same system, right? So one way to do this is to use a file, right? How many people have ever used a file to pass data between two processes, right? Or just had a file that one process read and another process wrote, right? How many people have ever linked processes together using pipes? A lot of you guys probably did this and didn't know you were doing it, right? So I can allow one process to consume the output of another process. That's another way of doing IPC. And then there's all these other ways to do it, right? I can use exit codes to allow children to communicate with their parents. I can use I can actually set up shared memory regions as long as both processes agree to do this, which allows both processes now to access the same memory, again, in a sort of a well-regulated way. And all of these have some semantics limiting the degree to which processes can sort of interfere with each other, right? And this is done because I wouldn't want some process on the system just to be able to kill off any other process, right? That would be suboptimal, right? All right. So let's talk a little bit, and this is something that I've done because I want you guys to sort of look at these slides and poke around a little bit on your own. How many people have ever had a chance to sort of do some poking around on like an Ubuntu or a Linux type machine, right? All right, cool. So the rest of you guys, you have one of two options, right? One is that you can download our virtual appliance, and then that machine is yours, right? Anything you do to it, anything you like, we won't necessarily be able to fix it for you if you bring it to office hours, but you are certainly, you are the master of that machine, right? Nothing you do to that machine will bother anybody else, and you're welcome to sort of do all these types of things to poke around with the processes that are running and sort of play with them, right? So one way of doing IPC is this idea of return codes, right? Return codes allow when I allow a relationship to be established between two processes, and when a process creates another process, which we'll talk about on Monday or Wednesday of next week, it allows the child process to communicate something to the parent, right? So here in my shell, what I've done is I'm going to sleep for 5 seconds, and then I'm going to run a program called bin true, right? And what the shell does, because I've run this in the background, is it's going to create this new process, and it's going to return to me the process ID, right? And then what I can do is, because I'm the parent of that process, I'm the shell, I can wait for that process to complete, which is the next thing I did here. And then what will happen is, and this command finished when that first process completed, right? I wish I could like do this in the terminal, which I probably could, right? And what it does is when it finishes, it tells me that it's done, right? And here you noticed, does anyone know what the program bin true does? By the time you guys are done with assignment 2, you will know what bin true does. Bin true and bin false are probably the simplest possible Unix programs you could write. Does anyone know, can anyone guess? OK, so it turns true or false, but what does that mean? How do we represent true? It's okay. I hear about 1/2, right? So good, true. I don't know if this is like an existential statement on Linux machines, is 0, right? It is not 1. 1 is false, right? So all bin true does is exit. It just exits normally, right? Which returns 0. What bin false does, it returns 1 in this case. And you can see that when I waited for bin false, the shell was kind enough to inform me that bin false had exited, but it also had returned the error code 1, right? Here, the shell didn't tell me anything because that was normal, right? Here, usually what happens is if I return a code that's not 0, it indicates that some sort of error took place, right? And so the shell is nice enough to tell me this, right? All right, so interesting. All right, and then if you've ever, I don't know, this is a little bit of sort of bash wizardry, right? But if you've ever run a program and then maybe it exited, you didn't know what happened, bash will store that variable for you in this special sort of variable name, right? So here I ran bin true, and I echoed the return code at 0. I ran bin false, echoed the return code at 1, right? All right, so let's talk about pipes, right? Pipes are, probably one of the most useful little sort of programming abstractions that was created by some of the sort of early Unix systems, right? Pipes allow me to set up, a series of sort of communicating processes that allow me to sort of transform data as it passes from process to process, right? So here's an example of a pipe. What is this particular command doing? Does anybody know? Should be pretty obvious. What's the first part of the command doing? What's that? Yeah, so PS is a tool that allows you to examine processes that are running on the system. I would encourage you guys to use this, either on Timberlake or on your virtual machine to get a sense of how it works. This set of options simply causes PS to print all the processes that are running on the machine, right? And then what's the second part of the command doing? Yeah, it's looking for my username, right? And in this case, it turns out that you can see that some of the processes that are running are actually owned by me, right? So this is the output from PS. This is the owner of the process. This is the process ID. We'll talk about this stuff more later. And then this is the command that was run, right? And it turns out there's actually a couple of processes that are owned by root that were returned simply because my username is actually in the name of the command, right? So pipes allow me to take output from one process and pass it on to another process, right? Again, this is a fairly simple form of IPC, right? It allows these two processes to communicate in a pretty limited way, right? I could probably pass some data to another process that would cause it to fail, that would be probably difficult to do, right? And pipes really exist to facilitate the sort of chaining together of small Unix terminal commands, which is the basis for a lot of programming on these types of systems, right? How many people are pretty familiar with this stuff? OK, good. Well, I'm glad I'm not going too fast. All right. So another way that we can communicate between processes is by sending a process what's called a signal, right? And a signal is pretty much what it sounds like, right? A signal allows one process to basically sort of reach out and tap another process. And because I'm a computer and not someone tapping you, right, I have all these different ways of tapping you, right? So I can tap you with different numbers, right? And these numbers have sort of well-defined meanings, right? So signals allow one process to trigger some execution in another process while the other process is running, right? So to make signals safe, right, on some level, this sounds very unsafe, right? You're telling me that any process on the system can basically send a signal to any other process. And that's not exactly how it works, right? But the other thing that we do to make signals safe, is we allow processes to configure how they're going to respond to signals, right? How many people have used signals before? OK, everybody should have their hand up, I'm pretty sure, right? How many people have used signals before? OK, you guys who didn't think you would use signals, what have you done before that you might think was potentially implemented using a signal? Man, don't just yell stuff out. I want to draw out the moment, yeah, so how many people have used Control-C? Yeah, there we go, OK. Control-C is implemented using a signal, right? What happens actually when you press Control-C is that bash, or whatever shell you're using, sends a signal to the process that's running, right? That signal has a specific name. It's called sigterm, right? That signal asks the process that's running to terminate, right? It is not a demand. It is a request, right? How many people have hit Control-C and nothing has happened? Yeah, so the process that receives that signal is not always capable of handling it properly. And if you want to, you can do this. Is this just me? Like when I was a kid, we used to have computers at school, and we used to messing with them, so they would print some stupid string over and over and over again in a loop, and the teacher couldn't turn it off, and so they had to cut power to the school. Maybe that's what happened yesterday morning, actually. Maybe someone did that at the computer level. Someone wrote a little basic loop, and they couldn't figure out how to shut it down, so they just cut networking to the entire campus. If you write a process, you can actually choose to ignore the termination signal, right? If you want to, you can just register a handler that doesn't do anything, right? Sigterm is sent by Control-C. It's actually on the slide, yeah. Sigkill, right? So what about sigkill? Can sigkill be ignored? Yeah, it's a little more brutal. I don't know who came up with these names, right? But that's pretty much what it does. Sigkill is a signal that it's actually the processes are not allowed to ignore, and it will definitely cause the process to terminate, right? Do you think you can just send sigkill to any process? You should go on Timberlake and try sending sigkill to a bunch of processes that you don't know, right? I mean, why not, right? What's the worst thing that could happen? You might get an email from someone, an angry email, right? Yeah, so sigkill is a signal that you have to have certain permissions to deliver to a process. Yeah?
So those have int values that you can accidentally override, right? Like if you write a signal handler that has sigterm signals,
Yep.
could you override that on accident?
Yeah.
Oh.
I mean, and by override, could I handle it in a different way?
Yeah.
Yeah, of course, right? I mean, sometimes people choose not to handle sigterm. Some programs will print like, I am ignoring your attempt to kill me, right? Which I guess is more polite than just doing it without telling you. But yeah, so yeah, you can, with all the standard signals, you can wrap them in your own handles. I think there's only a couple that can't be ignored. Sigkill is one of them, right? Sigkill will always be delivered and will always terminate the process, right? Yeah?
So when you send sigkill, there's no way to handle it and then exit the operating system?
I don't remember what happens. It can't be masked, but I think that when I'm trying to remember exactly how it's implemented, but I think either before or after sigkill is delivered, the operating system will terminate the process, right? It might be after, but there's no way to mask it, right? So there's no way for the operating system will essentially clean up the process as soon as sigkill is delivered.
Or
Right?
I guess, is sigkill actually a signal, or is it?
It's a signal.
Or is it like an operating system?
No, it's a signal, but I do think it triggers some special behavior in the operating system. I'll look it up and get back to you. That's a great question. Right. And you can, if you've ever had a problem trying to get something to exit, you may have done kill-9, right? 9 is the signal number for sigkill. Right? All right, so we're gonna come back to IPC. We'll talk a lot about return codes when we start getting into the system called interface, particularly wait and exit, which is where return codes get used. And your guys going to implement return codes for assignment 2, right? So you'll get sort of intimately familiar with how they work, right? Pipes we'll talk about when we talk about fork, right? A lot of these are stuff that's bound up in the Unix system call interface, right? Signals, not something we're going to talk about too much anymore. Signals end up having a lot of sort of interesting implementation issues, particularly with regards to threads. So not something we're going to talk about too much more, but just something sort of fun to know. And again, we'll come back to shared memory when we talk about address space a little bit later, right? So I want to clear up some confusion, before, because we'll move on from talking about the system call interface to talking about how the operating system multiplexes the CPU. Processes and threads, right? So one thing that can be confusing about this terminology is we can refer to both the process and a thread as running, right? We talk about a process is running typically when one of the threads it contains is running, right? We talk about a thread running when that actual thread of execution is executing on the CPU, right? And again, so a thread of execution really is tied to the CPU state, whereas a process or a task, application, job, program is this more broad category, right? And every thread has some process that it belongs to, right? And we're going to actually talk about this, right? OK, so let's go through an example of a process and talk about how a process sort of uses these various system resources, right? So let's say I look at Firefox, right? And again, I shouldn't say this. I tease myself a lot about using Firefox. How many people still use Firefox? Oh, wow. OK, so I always think I'm sort of a fuddy-duddy because I don't use Chrome or whatever, Platinum or whatever the new browser is or whatever. But I like Firefox. So I use Firefox. So if you look at Firefox while it's running, you'll probably find that Firefox has a bunch of different threads running, right? What are those threads doing? What would you guess? You open up Firefox, it's got 16 threads going, right? What are some of the things that those threads could be doing, right? Yeah.
Running plugins and
Be executing like a plugin, right? What else? Yeah.
Tab management.
What's that?
Tab management.
Yeah, a lot of times there might be like at least one thread per tab, right? So every time you open tabs, there's a thread. But what is the thread doing for that tab? Yeah.
It's storing information on that tab, like the physical. What is that tab showing?
writing things to the screen.
It's rendering HTML, right? You know, some things got to take that, you know, text that you wrote on your web server and actually convert it to these beautiful images, right? That's, you know, what these threads be doing. What else? Yeah, it could be. So when you go to a web page, right, frequently web browsers will fire up a bunch of threads to actually fetch data separately from all the different sources, right? So, you know, you need one thread to get the content for the web page, and then 6 threads to get all the different ads that have to be pasted in all over the web page, right before you're allowed to see it, right? Or like random YouTube video streams and, you know, cats with whatever. Cats, lots of cats, like 4 cat threads and then a thread or 2 to do everything else. Yeah, so all sorts of things, right? So, you know, we load web pages in parallel. You know, we actually redraw the screen. That's the other thing that we didn't get to, right? You know, how do you think the mouse moves around, right? You know, there's a thread or maybe multiple threads that are essentially in charge of painting, right? So when you click on a menu in Firefox, something's got to paint what the menu looks like, right? So this is the type of thing that Firefox would be doing, right? Firefox uses memory, sometimes a lot of memory, right? What does Firefox use memory for? What are some things that Firefox would have stored in memory? Yeah. Yeah, like parts of the page. What else? Cookies. Man, apparently a lot of people have lots of cookies in their web browser. Yeah, like session state, right? So, you know, so that would be cookies, yeah. Yeah, like, you know, JavaScript needs memory to run. So when you download pages or when you run pages, you have these little programs now they're embedded in that are running. Yeah. Okay. History. Where do you think history would be? It could be in memory. It could also be where? In a file, right? So that when you open up Firefox again, there it is, right? Certainly things like bookmarks are going to be stored in files. Yeah. Yeah, if you're playing you know, a lot of times people are using Firefox almost like an operating system now, so they're playing videos, doing all sorts of fun stuff. So I think we have enough stuff, right? What about the executable of Firefox itself? Nobody thought of this, right? That code lives somewhere, right, when it's loaded in, and it actually lives in memory. Firefox also uses shared libraries, right, like probably an HTML parsing library, JavaScript libraries, all sorts of things. And then, you know, a lot of the stuff that you guys talked about are things that are going to be stored either in the stacks of the threads that are running or in dynamically allocated memory, right? So stuff, right, content, right, but also the code that Firefox is running. Why would Firefox have files open? What sort of stuff other, you know, history could be stored in files? What else would be stored in a file? What other stuff would I want to persist? Yeah.
Images also. Bookmarks.
OK, so bookmarks would be stored in a file. I want that to persist. What else does Firefox probably store in local files? Yeah. Cache. Yeah, the cache of your browsing history, so it doesn't have to keep reloading stuff from the internet. What else?
Add-ons.
Yeah, you know, plugins that you've installed, things like that, preferences, you know, anything that you want to persist between different runs of Firefox, right? All right, so let's use some of the tools we talked about to look a little bit at Firefox, right? So, but let's actually, I guess we're going to do this for Bash, right, rather than Firefox, all right? So Bash is a shell. How many people use Bash? OK, cool. So I'm going to use PS to look for my bash process, right? And this gives me 2 entries because it also returns the grep that I just ran. If I wanted to do this more simply, I could just run pgrep, right? But here's the actual bash process, right? And PS can actually give you all the threads that are attached to that process, right? In this case, it's only showing me 1, right? Why, you know, Firefox has got all these threads. Why does bash only have 1 thread? What's that? What's wrong with bash, man? Yeah. Yeah, it's a shell, right? I mean, I would be worried if bash had like 6 threads open. What are you doing, right? You know, like it's animating the background, right? It's new bash 2000, right? Yeah, so I mean, bash is a pretty simple program. You type something and then it does something for you, right? So it doesn't have to do a lot in the background. All right, so let's start filling this in for bash. So here's bash. It's got 1 thread, and it has a process ID. Actually, sorry. So this is, let me try to get through this in the next 5 minutes. So this information is stuff that we can get from the PS output, right? So this is the user ID, that's me, right? This is the person who's running the process. Every process is a process ID. What do you think well, I just told you. I'm rusty with these slides. The parent process ID, right? So that's the process that spawned bash, right? What do you think PRI is? Priority, right? Some information the operating system uses to schedule bash. What about size? The size of what, though? It could be the size of anything, right? It's the size of bash's name. No, this is the size of the core image of bash, right? So this is the bash executable. It's only this big. It's pretty impressive, right? It's only about, let's see here, only about a meg. Pretty good for a full-featured shell. What about WChan? Okay, it stands for waiting channel. What is a waiting channel? How many people have started assignment 1 already? No. Yeah, Victoria did. You should be able to answer the question. What's a wait channel? It's a place for threads to wait, yeah. What would it be waiting for on a waiting channel, potentially? What's that? No. It could be, right, it could be waiting for another process to finish, a process that I spawned through bash, right? It could be waiting for I/O, yeah. Yeah, basically resources, right? So if the process was not running, this tells me what it's waiting on, right? In this case, bash was actually on a wait channel, and I think the reason for this is because when I ran this, it was waiting for grep to finish, right? Because it had spawned this, right? RSS, now we're getting into real esoterica. RSS. What is that? What does it stand for on the internet? I have no idea. Real simple syndication. No, not so much. This is the amount of memory that's in use by the process. The amount of memory has resident, right? And then time. Times it is initiated. No, it's actually the measure of the amount of time the process has spent running, right? And I think if I remember correctly, this is actually running as in using the CPU, right? So even if I've been using bash for hours, this number might be very small because a lot of times, what is bash doing? It's waiting for me to type something, right, and hit enter, right? So bash doesn't have multiple threads. We just covered that. We've got one thread in bash. Yeah, I'll just jump to the chase here since we're running out of time. I was looking for a process on my web server with a bunch of threads. Apache, right, of course, right? Does anyone know what Apache is? It's a web server, right? And web servers have multiple threads because they spawn frequently one thread for each, or they use one thread to respond to each request, right? So when you contact a web server, it responds to your request using one thread, right? That isolates that response from the other threads that are serving responses to other clients. All right, so when I was putting together these slides, I had a lot of fun learning about all these cool tools. How many people have used PMAP? Ah, there we go. PMAP's cool. PS is cool. PMAP is also cool. PMAP actually will dump the memory mappings of the process, right, which is pretty neat. So it'll tell you, and this is not going to make much sense today, but it will much later, what addresses in memory the process is using for what, right? So what do you think this is right here, right? So this is telling me this is the address, and this is going to be in certain increments. And then this is some information about what's loaded there. So what are these first sort of 3 areas for? Yeah. This is the program, right? And in particular, look at this first segment, right? So this is 876K. Remember, bash was about a megabyte in size, right? If you guys have used Unix, you could probably recognize these. What are these? These are permissions. And what does this mean about this segment of memory? I can read and execute it. So what do you think's in here? This is bash's source code, right? This bash has loaded its code into memory, and the code that it's using is loaded in this part of memory, right? What do you think's in this? So now I have this. These two are a little bit more interesting, right? This tells me that they came from bash, right? They came from the bash executable file, but this one is marked read only, and this one is marked read write. So what do you guys think is in the read only segment? What's that? No. Remember, this came from the bash executable, not from my file. Yeah. No. You know? Constants, exactly. Any sort of statically defined variable. So if you ever define a variable in your code, right, as a constant, can't be changed at runtime, this is where these end up, right? And then what about this area? This is sort of a larger area, but oh wait, sorry, up here. This is a larger area. It's marked as read-write, right? What's that? No, these are not executable. Right? I can't execute stuff, so there's no code in these regions. Yeah. Nope. Remember, this came, well, they could be preferences, right? They're global variables that are modifiable, right? So here are some global variables that are not modifiable, and here are some ones that are modifiable, right? Let me skip down to here. We're almost done. What's in here? So this is farther down in Bash's address space, and it's telling me that now what is this? This is a shared library. What library is this? That's the friendly C library, right? So Bash has loaded the C library into its address space, and it's using code from the C library to do things, all right? So on Monday, we will finish this Bash example, and we will keep talking about processes. Have a good weekend. Please get started on the assignments if you're worried about the class. That'll give you your best chance to get a sense of whether or not this is a good fit.